Okay, so I am Dr. Rachael Livermore. I'm an astrophysicist at the University of Texas here in Austin, and I like to make fun of movies. So as much as I love this movie, we're going to make fun of it a little bit. But it's okay, we're only making fun of the science, and it's not like they were taking that terribly seriously anyway. So let's dive in right at the start of the film, where we're in a simulator heading towards Gamma Hydra. Now Gamma Hydra is a real star. It's the third brightest, Alpha Beta Gamma, in the constellation Hydra. And this is an image of the constellation Hydra, and I'm sure some of you can pick it out. But for the rest of us, I'm going to add the stellarium artwork. You can see that gigantic snake right across the screen. And this one right down in the tail there is Gamma Hydra. So this is a real star, which is apparently on the edge of the neutral zone. It's about 130 light years away, so which is pretty far. I mean, even in Star Trek universe. So in Star Trek, the original series, they invented warp drive because obviously in real life, you can't flick between one planet and the next on a weekly basis. So you've got to go faster than light. Fine, I'm not going to quibble with that. However, even in the original series, warp drive had rules. And there is actually an equation for how fast they're going. It's the warp factor cubed times the speed of light. And they never really go, they're usually warp factors of a few. They never really go above 10. As of the next generation, they actually set a hard limit at 10. So let's use 10 because the math is easy. If you're going warp 10, that's 1,000 times the speed of light. So it should take about a month and a half to get to Gamma Hydra, which I don't really think is implied, but whatever, we're in a simulator, so who cares? For some reason, they fit explosives in their simulators. I'm not really clear on why you would do that, but especially since they're putting all their cadets through this. I mean, the bills to repair that thing must be monumental, but at least all the teachers are getting lots of acting practice, so that's good. So while we're still in the simulator, there's another cool little math thing that I picked up on.
Project parabolic course to avoid entering neutral zone.
Aye, Captain. Course change projected.
So it was a really boring offhand line, right, that no one else paid any attention to. But if you're a math nerd, then you know what a parabolic course is, and it gives me an excuse to talk about conic sections, which are really, really cool. I promise. So conic sections are, as the name implies, the shapes you get if you slice a cone at different angles. So if we start up there at the top left, if you slice a cone completely flat, you get a circle. If you tilt that slightly, you get an ellipse, which is just, a circle is just a fancy kind of ellipse. If you tilt it even further, say look at the bottom left one, you're going out the bottom of the cone, so you now have an unbounded curve. You get a parabola or a hyperbola. Now, the thing that's cool about conic sections is if you're in orbit around a planet or experiencing gravity, you will follow one of these curves. So as we're on a planet, we're in orbit around our sun, we're following an ellipse. It's actually very, very close to a circle, but technically an ellipse. And this is good because this is a bounded curve, and that means we keep going around in orbit and we're not going to fly off into space and get very dark and very cold. If we were going a bit faster, instead of following an ellipse, we would follow a parabola, or faster still, a hyperbola, and we would whip around the sun and go zooming off in the opposite direction. So if you're using a gravity assist, which we've talked about at a few of these movie screenings, then what you're doing is following usually hyperbolic trajectory. So you're going to zoom in close to a star or planet or whatever, whip around it and go off in the other direction. You don't want to enter a closed orbit. So a parabolic trajectory is interesting because a parabola is a very, very special curve where you have to be going exactly the escape velocity. So exactly the velocity you need to escape the gravity of your planet or star, or it's unclear exactly what they were whipping around. But fine, it is actually mathematically correct. And for a little offhand line of technobabble, I thought that was pretty neat. But then I am a nerd, so...
It's about you flying a goddamn computer console when you want to be out there hopping galaxies.
Spare me your notions of poetry, please. We all have our assigned duties.
Paul.
So I understand that this scene is just McCoy being McCoy, and we're not supposed to take anything he says terribly seriously, but it's one of my biggest pet peeves in science fiction, so I clipped it anyway. He says something there about he's berating Kirk for being miserable on his birthday and says you want to be out there hopping galaxies. Kirk has never hopped galaxies. No one in Star Trek has hopped galaxies, except in the original series episode by any other name where some aliens from Andromeda come and visit our galaxy. But it's specifically acknowledged in that episode that Starfleet does not have the technology to do that. It would take thousands of years to get to another galaxy, and that's because I often talk about space being big, but all of space that we see in Star Trek is only within our galaxy, and space in between galaxies is even bigger. So here's a diagram of our local group. This is like our local village of galaxies. The Milky Way is down there in the center. Now each of these rings, as we go outwards from the center, marks 2 million light years. So remember I said that 130 light years was kind of far away? Our nearest comparable sized galaxy is Andromeda, which you can see just up and to the left a bit of the Milky Way in the center. That's 2.5 million light years away. No one is going there, even with warp drive. So no, Kirk has never been out hopping galaxies. Sorry, Bones. Now, as we get into the main plot of this movie, the first glimpse we see of SETI Alpha 5 is from the spaceship Reliant, where Chekhov is going to check it out. So SETI Alpha is also kind of a real star. I say kind of because that's not how our naming convention works quite, but there is a real star called Alpha Ceti, which would be the brightest star in the constellation of Cetus. This one is a little bit easier to find because some of you may have already picked out Orion over on the left-hand side. So this gives you some kind of a signpost, but let's fill in stellarium artwork again. And you can see if you go from Orion down and to the right a bit, then right there, this is Alpha Ceti. So is this the star that SETI Alpha 5 is orbiting? I don't know, but it's my best guess, so why not? And because it's a real star, I can say something about it. It's actually a red giant. So this is a star that's used up all of its hydrogen and is at the end of its life, which means it gives me an excuse to talk about the life cycle of a star. So this is how stars are born. You start with your star-forming nebula in the middle, which is a big cloud of gas and dust. We're going to come back to nebulae later. And if we follow, say, a sun-like star, so let's move anti-clockwise from our star-forming nebula, you get a sun-like star. Stars like our sun are just hanging around, burning mostly hydrogen into helium and giving off light as they do so, and also heat, which is handy. But eventually they run out of hydrogen, and so they start to cool down and swell up into a red giant. This is something that our sun will do eventually, possibly swallowing the Earth as it swells up, but humans will be long dead anyway, possibly within the next couple centuries, who knows. Eventually, the outer layers of this red giant drift off into space and form a planetary nebula, which has nothing to do with planets, it's just a really confusing name. And in the center of that planetary nebula, you have the remnant of the core of the star, which is a white dwarf. So that kind of drifts off the bottom of my diagram here. But the rest of that nebula then becomes a star-forming nebula again, and on goes the circle of life. You also get bigger stars over on this side. If you're much bigger, you have a much more lively life. You live fast, you die young, you burn a lot hotter, a lot brighter, and then instead of just drifting gently off into space, you explode in a supernova. But this star, SETI Alpha or Alpha Ceti, is a red giant. So it is possible to have habitable planets around a red giant. They would not be the same planets that were habitable when this sun was undergoing its normal lifespan as what we call a main sequence star. Because as the star becomes a red giant, although it cools down, it swells up so much that it's actually giving off more energy. So you want to be further away to be the right temperature than you would be when it was a main sequence star. But assuming it's been a red giant for long enough, fine, there could have been a habitable planet called Ceti Alpha 5 at one time around that star. However,
This is Ceti Alpha 5!
that was just an excuse to show that clip. We hear from Khan that the nice habitable planet that he was left on, Ceti Alpha 5, has become slightly less hospitable in the last 15 years, thanks to the explosion of Ceti Alpha 6, which messed all the orbits up. So, to give them some credit, yes, if a planet exploded, it could affect the orbits of other planets around it, and changing the orbit of a planet will change its habitability. So, okay. However, we just talked about the life cycle of a star, so let's talk about how we form planets. Planets are pretty boring, really, says the person who works on galaxies. You have this same star-forming nebula that your star came from. It collapses and forms a star, and some other debris around that star collapses and forms things that are not massive enough to burn, and they become planets, they become bits of rock, asteroids, comets, all sorts of things. And they're not burning anything, so they don't do anything after that. They just kind of hang around. Unless, you know, if they get swallowed up by the star, then I guess you could melt them or whatever. But generally, they're just going to hang around being very boring and very planety forever. So the big question I have about this movie is, why did Ceti Alpha 6 explode? And why is no one else curious about this? Because this would be a really strange astrophysical phenomenon, and I really want to know more. But this is actually a common thing in Star Trek, and it's a shame we can't go right on and do Star Trek 3, because they seem to have this idea that planets evolve in a way that involves them breaking up eventually somehow, and maybe exploding. I really, really want to know where they get that idea from, because it's kind of scary, and I'm maybe missing something. So while we're talking about planets, obviously a lot of the plot of this movie rests on the Genesis device. The idea of the Genesis device is that you introduce it to a planet, and it rearranges matter at the subatomic level to make this lifeless rock into some kind of thing that can host life. So if we think about what would you need to do to a lifeless planet to make it habitable, one of the most important things that determines whether or not a planet can be habitable is actually its mass. You need to have the right amount of gravity. If you don't have enough gravity, then its atmosphere is just going to drift away. There isn't going to be enough gravity holding it in place. So you can keep pumping as much oxygen as you want into this thing, it will just drift away into space. So you want enough gravity, but you don't want too much, because then you're not going to be able to pump blood around your body and you're going to pass out and die. So there's a very, very narrow mass range, which is the Earth plus or minus a factor of 2 pretty much, that's comfortable to host life. Now Carol Marcus does say that the Genesis device transforms matter of equivalent mass. So we're not changing the mass, which means you have to have already picked a planet of about the right mass to be habitable. So what's going to be wrong with a planet that has the right gravity but is currently lifeless? The most likely thing is it's going to be the wrong temperature. So either too close to its host star, so it'll be too hot and all the water will boil, or too far away so it's too cold and you don't have liquid water. So it needs to be in the right orbit around its star, otherwise, again, you can make it full of life, but it's not going to last very long. And it doesn't seem to be changing that particularly. The planets seem to stay in basically the same location. So what else do you need? You need an atmosphere. The atmosphere of Earth is mostly nitrogen, with about 20% oxygen. The oxygen is the stuff we need. The nitrogen, luckily, is inert and doesn't hurt us. So you need like something similar on a planet that's going to host life. And so you can transform, you can't. In Star Trek universe where they have transporters and we're accepting that they can rearrange matter, fine. You can rearrange matter into the right kind of atmosphere you need for your planet. And then pretty much job done. There's some other details. You need a magnetic field so you're not getting blasted by all this radiation from the sun, little things like that. But there's nothing else really fundamentally about the planet that you want to change at a subatomic level. So I actually think this Genesis device is kind of overkill. All they really need to do, they've got a planet that's roughly the right mass, right position around its sun, blast it with some oxygen somehow, convert its atmosphere into chemicals that are more useful for life. Job done, right? But for some reason, they need to transform the entire planet. So I guess they're actually creating the life that's going on the planet as well. They seem to create a lot of trees on the planet we see at the end. I'm generally very confused about how the Genesis device works. But like I said, this is the Star Trek universe where, because of the existence of transporters, we accept that they can rearrange matter that carefully. So, fine, whatever.
Ah, Kirk, my old friend. Do you know the Klingon proverb that tells us revenge is a dish that is best served cold? It is very cold in space.
Again, any excuse just to clip these really great Khan lines, right? So how cold is it in space? Does anyone know? Very. So it actually depends entirely on where you are. The thing about space, again, something that's come up in a few of these movie screenings, is there's no air. So there's nothing that's transporting heat away from you and evening out temperature. So if you're close to the sun, say maybe like in orbit around the Earth, and the sun is shining directly on you, it's actually going to be really, really hot, uncomfortably hot, hundreds of degrees hot. On the other hand, if you're in shade, so say you're on the night side of the Earth, it's going to be really, really freezing. So let's assume you're in deep space, you're far away from any star, or you're on the night side of a planet or whatever, and so how cold can space get? So this is actually set by the Big Bang, which is pretty cool, which gives me an excuse to talk about the history of the universe. Yay! This is more what I work on, and it's cool. So this is what we understand about the history of the universe. Starting way over on the left-hand side, we have this Big Bang. The first, 10 to the minus 40 seconds or whatever, a bit of a mystery. But after that, we have a pretty decent handle on it, considering we're just little carbon-based life forms on one little rock in one galaxy. It's actually pretty cool that we figured this much stuff out. So you start off shortly after the Big Bang with this soup of particles. And to begin with, everything's very, very dense, so no light is escaping. And gradually, as the universe expands, this matter spreads out enough that light can escape. And this point at which light was able to escape, we call the surface of last scattering. And you can kind of see that as a kind of greeny, bluey thing way over on the left-hand side. After that, you start forming atoms. So instead of just having random quarks and electrons, things combine together, they form atoms, mostly hydrogen. And eventually those hydrogen atoms clump together under gravity and you get stars and galaxies and the Alamo Drafthouse and beer, and it's all good. But the really cool thing is that that surface of last scattering is still visible to us today. And it permeates all of space as what we call the cosmic microwave background. This is an actual image of it, taken with WMAP. There's actually a more recent one, but I still think the WMAP one is prettier, so there. What you're seeing here is the energy density fluctuations over the entire universe. So if you've ever seen a projection of the Earth in this kind of oval shape, this is the same thing. So we're looking at space as a sphere around us and projected into this oval shape. And the really dense regions show up in red and yellow. These are areas where there's going to be a lot of mass, there's a lot of energy density. And the really not dense areas are darker, like blue and almost black. So this looks as though there was a lot of difference between different regions in the early universe. This is about 300,000 years after the Big Bang. But this image is hugely exaggerated. This is an incredibly sensitive telescope. And the difference between the very hot and the very cold regions of this map is about 1 part in 10 or 100,000. So the universe is actually very, very even at this point. Now, of course, 300,000 years after the Big Bang, it was also really, really hot. But since then, the universe has expanded, and this has cooled down. And so this cosmic microwave background, as we see it today, is about 2.7 degrees above absolute zero, which is extremely cold. So when we talk about space being cold, this is the limit of how cold it can get. If you're far away from any stars, then all you're feeling is this base remnant of the Big Bang, which is 2.7 degrees above absolute zero. It's very, very cold in space.
Why are we slowing? Daren't follow them into the nebula, sir. Our shields would be useless.
So this is my favorite rant about this movie. And it's about the concept of a nebula. And this is something that Star Trek is weirdly preoccupied with. So if we fast forward 34 years from this movie, who saw Star Trek Beyond that came out last year? Ooh, who saw it with Astronomy on Tap? Yay, some people. It was great. I actually like this one. I'm not a big fan of the Abrams movies, but I thought Beyond was great. But it had this scene in it.
Our mission is straightforward. Rescue a crew stranded on a planet in uncharted space. Our trajectory will take us through an unstable nebula, one which will disable all communication with Starfleet.
So it's possible that this was just a reference to the Mutara Nebula in Wrath of Khan. There were a lot of old school Trek references in that movie. But what is it with these nebulae and lightning? There's an image of a real nebula. Notice the distinct lack of lightning. I really don't understand where this has come from. So we already discussed what a nebula is. It's just a big cloud of gas and dust that's forming stars. You can see in this image some of the new stars that are being formed in this nebula. And it looks kind of dense because, you know, most of the really pretty pictures you see from like the Hubble Space Telescope, this is from the VLT, very large telescope, because astronomers should not be allowed to name anything, which is down and chilling. And so it looks like these are really, really dense areas of gas, but telescopes are really sensitive, and they're really not. So there's no such thing as a vacuum in space. Even the depths of deep space have stuff in them, where stuff is mostly hydrogen. And it's around the order of 1 atom per cubic centimeter. So I would never normally show a logarithmic plot in a public talk, but you're going to see why I have to for this one. So here we have about 1 atom in every cubic centimeter. Now every 1 on this y-axis is a factor of 10. That's what makes it logarithmic. So if we go up by 1, we're actually multiplying by 10. We started at -1 here, and we're going to go up to 5, so that's 6 orders of magnitude. That's a factor of 1,000,000. So a dense nebula is 1,000,000 times denser than empty space. That's pretty dense, right? Okay, so fair enough, that could mess with your shields, right? But anyone who's seen me rant about this before knows what this is. This is a quadrillion times more dense than a dense nebula, and it is air. So this is why it's relevant that they brought this scary nebula thing up again in the reboot movies, because in the reboot movies, specifically Into Darkness, and that's the only time I'm going to reference that that movie even exists, we saw that the Enterprise can operate perfectly well, not only in air, but even in water. So I have no idea why they're so terrified by these nebulae, but I guess it makes for a fun movie. So
he's intelligent, but not experienced. His pattern indicates two-dimensional thinking.
I just really like that line, mostly because it reminds me of scenes like this one in Futurama.
Our peace ring has him trapped like a tiger in a washing machine.
Get ready!
Looky here, looky there. Okay, watch
Okay, people,
yourself,
hold
watch yourself.
tight.
Here they come.
When you were planning this peace ring, didn't you realize spaceships can move in 3 dimensions?
No, I did not.
So yes, apparently neither does Khan. So I'm skipping over another thing that happened in this movie because we don't need to talk about that. And let's go right to the end, where we get this lingering shot, possibly setting up a sequel, do you think? But this shot raises so many questions. First of all, what are they making their coffins out of that it can survive re-entry into a planet's atmosphere? Second of all, this thing has fallen in from space, somehow survived re-entry, and not disturbed a single leaf on any of those plants. Where's the gigantic crater? I mean, I'm happy because it means that the contents of that coffin are okay, but so many questions. And I really, really wish we could go on and do the next movie. If I had any faith that anyone but me liked that movie and would actually buy tickets to go see it, then I would do it. Because there's so much weird planetary evolution stuff in it that I don't understand. But instead, we are going to come back next month and changing tack again to some proper classic science fiction. We're going to do 2001: A Space Odyssey, which is awesome, but an even awesomer book. So if you have time before Wednesday, August 16th, 2017, get the book. You can get it on Kindle, read it, it's amazing, and then maybe you'll be able to follow the movie. It's the only reason I can. Anyway, it's an awesome movie. I hope to see you back here next month. This is actually going to be our penultimate movie screening. So I am leaving the country pretty soon. So we're going to do this one more after this, and then that's it. But I want to thank you very much for coming out tonight. I've wanted to do this movie for a really, really long time, and they finally let me. So I'm really happy about that. Thank you so much for buying tickets, because that's the only reason that I'm allowed to do this. And thank you to the Alamo Drafthouse for hosting us, to Khan for introducing us, and to Lara for coming out and filming this for YouTube for people who couldn't be here tonight. I will be in the bar for a while if you want to rant about this movie, or more likely talk about how great it is. Or if you have any questions about science, that's what I'm here for. Other than that, have a very good night, and thank you.